So hello guys, in this video I'll talk about the chapter 4, that is the internal equilibrium condition. And in this chapter we'll talk about the hydrostatic equilibrium, and we'll talk about the mass continuity relation. Then we'll talk about the radiative and the conservative energy transfer and the temperature gradient. Okay, we'll derive this relation. Then I will do some numericals from this chapter. Okay, so what is the temperature? So before I start, I want to discuss some topic. Let me discuss first what is temperature gradient. So what is the temperature gradient? To define it in a very precise manner, I can define it as this is a physical quantity, okay, which describe in which direction and at what rate the temperature changes. Okay, so to write it down, so temperature gradient is physical quantity that defines in which direction and in which rate the temperature changes the most rapidly around a particular location. And it also has a dimension. The dimension is it is usually expressed in degree per unit length, so the unit will be the Kelvin per meter. Okay, so this is the temperature gradient. The definition is enough to understand what does it means. So if you going in a, if you are running, then the cold air just rushes out in front of your ear. Okay, so that is that is temperature is going, or the wind is blowing past your ear, then you feel cool. Okay, so that is also a temperature gradient. Or the refrigerator, you can take the example of the refrigerator. Okay, the hot air is going out, then cold air is rushing in, that is also temperature gradient. Okay, so now the another thing I want to discuss about you is that the hydrostatic equilibrium. So what is the hydrostatic equilibrium? Consider that this is a star. Okay, so this is a huge star. Okay, consider it as a sun. Okay, so okay, how does it stay that big, or how the gravity cannot collapse or does not collapse the star? Because uh, we know that gravity pushes it inward. Okay, but it is it is then be the effect is then cancelled by the pressure from the inside, that is due to the nuclear reaction that is ongoing every time. Okay, so the pressure created by the nuclear reaction, it maintains it into the equilibrium positions. Okay, so it does effect cancel the effect by the gravitational pressure, and it maintain the shape of the star. So if in case the nuclear reaction slows down, के हुन्छ न्युक्लियर रियाक्सन के भयो, स्लो भइसकेपछि प्रेसर पनि के हुन्छ, कम हुन्छ. कम भइसकेपछि नाउ अब के हुन्छ, अब यो ग्राभिटीले इट फर्दर के हुन्छ, यसले के गर्छ, पुस गर्छ स्टारलाई. ओके, सो फर्दर पुस गर्नु भनेको चाहिँ नाउ द डेन्सिटी अल्सो राइज एन्ड द टेम्परेचर अल्सो राइज. ओके, सो डेन्सिटी पनि के हुन्छ, बढ्छ, टेम्परेचर पनि बढ्छ. ओके, सो प्रेसर कम भयो बिकज न्युक्लियर रियाक्सन स्लो डाउन. अनि न्युक्लियर रियाक्सन स्लो हुने बित्तिकै प्रेसर कम भएर के गर्यो, यसले ग्राभिटीले यसलाई कल्याप्स गर्न थाल्यो. कल्याप्स गरिसकेपछि डेन्सिटी पनि बढ्यो र टेम्परेचर पनि बढ्यो. सिन्स डेन्सिटी र टेम्परेचर दुइटै बढिसकेपछि now it will start the nuclear reaction. Okay, so जुन स्लो डाउन भएको न्युक्लियर रियाक्सन के हुन्छ, अब इट स्टार्ट टु राइज अप अगेन. यसको रेट फेरि बढ्छ. किन यसको रेट बढ्यो? बिकज ड्यू टु द फ्याक्ट द्याट द ग्राभिटी स्टार्ट टु स्क्विज गऱ्यो भने टेम्परेचर बढ्योपछि डेन्सिटी बढ्यो, डेन्सिटी र टेम्परेचर दुइटै बढ्यो भने जुन स्लो भइरहेको रियाक्सन अब के हुन्छ, नाउ इट स्टार्ट टु गेन इट्स मोमेन्टम एन्ड इट्स स्पिड. अब त्यो भइसकेपछि फेरि के हुन्छ, प्रेसर बढ्छ. प्रेसर बढिसकेपछि देन इट स्टार्ट टु पुल आउटवर्ड, र यो के हुन्छ, सेप मेन्टेन भइरहेको छ. सो द्याट इज द हाइड्रोस्ट्याटिक इक्विलिब्रियम. सो हाइड्रोस्ट्याटिक इक्विलिब्रियम इज अ automatic mechanism by which the shape of the star is maintained. Okay, so के हुने भयो, यदि न्युक्लियर रियाक्सन स्लो हुने बित्तिकै के हुन्छ, यसले इनवर्ड पुश गर्छ, सो द्याट द डेन्सिटी र टेम्परेचर इन्क्रिज हुन्छ. सो द्याट न्युक्लियर रियाक्सन फेरि के हुन्छ, तपाईँको रेट बढ्छ. रेट बढेपछि देन इट स्टार्ट टु गिभ द आउटवर्ड प्रेसर मोर, र साइज के हुन्छ, मेन्टेन हुन्छ. र एकदमै धेरै न्युक्लियर रियाक्सन भयो भने देन द टेम्परेचर अल्सो डिक्रिजेस एन्ड द प्रेसर अल्सो डिक्रिजेस. नाउ द न्युक्लियर रियाक्सन स्लोज डाउन. ओके, स्लो भइसकेपछि अब बाहिरबाट प्रेसर धेरै हुन्छ. नाउ अगेन इट कम्स टु द original shape and size. So that is the hydrostatic equilibrium, which is a very I think it is a very effective mechanism. It is a self-automated mechanism by the star that it maintains its regular shape. So that is the hydrostatic equilibrium, guys. So now to go back to our derivation point, so how do I can calculate the hydrostatic equilibrium? What is the formula for the hydrostatic equilibrium? Consider that force of, let's consider that there is a small cylinder. Okay, just take the small part of the cylinder. Okay, let me call this dm. Now what is the force? Force is given by gm by r square, and then instead of writing small d, I'm just writing dm. Okay, so I can write it as, then since the density is mass by volume, then mass will be equivalent to density into volume. So it will be equivalent to density, and instead of writing volume, I can write it volume as dr into dA. Okay, so that is first equation. In second equation, consider that यो दुईटा सेक्सन लिनु. ओके, यहाँ तल सेक्सनमा चाहिँ प्रेसर, यो माथि चाहिँ डिपी छ, तल त के हुन्छ प्रेसर बढ्दै जान्छ. ओके, plus P. So this is not dP, this is P, and this is P plus dP. So यो सेक्सनको प्रेसर कति हुन्छ त dP हुन्छ. Okay, and I know the formula for the force, the pressure into area, so that will be equal to dP into dA. Okay, so instead of writing this, I can just simply write it as dP and the dA. Okay, now के हुन्छ, यो dA र यो dA काटियो. ओके, सो फाइनली यो dr यता जान्छ, देन dP by dr is equal to minus gm by r square, and then it is given as rho. Okay, so this is the equation of the hydrostatic equilibrium. So then there is another condition, that is the mass continuity equation. So what is the mass continuity equation tells us? It is simply, it is derived as dm by dr, which is 4 pi r square, and then it is the density. So these are the two very important equation, guys. You must remember these two equation, because we're gonna use this equation a lot. Okay, so the important question that will be asked in the exam is to derive the radiative and conservative energy transport. Okay, so let me first derive the radiative part. Okay, so I'll just derive the radiative part. Okay, so from the radiation, before we proceed, हामीले अगाडि के निकालेको थियो? Previously we found that the radiation pressure is 1 by 3 AT to the power 4. So this is the radiation pressure. I know that luminosity is given by 4 pi r square and then f. Okay, so that is the luminosity that is given by. So instead of writing that luminosity, what I can do in place of luminosity, I can write it as force can be written as 4 pi r square. This is energy upon area into time taken. Okay, so force भनेको त्यो भयो हैन. अब यो 4 pi r square, एरिया एनर्जी भनेको फोर्स इन्टु डिस्टेन्स हो. ओके, डिभाइड बाई एरिया इन्टु टाइम हुने भइहाल्यो. ओके, अब त्यसमा त दुई मत छैन होला हैन. नाउ दिस फोर्स बाई एरिया, यो फोर्स बाई एरिया भनेको के हो? द्याट इज द प्रेसर. ओके, सो द्याट इज द प्रेसर. देन इज 4 पाई आर स्क्वायर pressure, and then d by t is equal to the, it must be equal to the velocity, but in this case in free space it is velocity, but in the interstellar medium, that is inside the star, it is given by c by t. Okay, so what is the t? T is the optical thickness, and this is always equal to t is equal to minus alpha dr. What is alpha? Alpha is the optical this is the opacity. Okay, this is the optical thickness, this is opacity. Okay, so this is L है. So this is यतिसम्म derive गरिसकेपछि Now what I can do is I can just simply write LR by C. Okay, so this is a general case, 4 by R square. So instead of writing this T, म यसलाई के गर्छु, I'll just write like first I'll just take the derivative. Okay, so this is minus 4 pi R square. Okay, then this is dp by dt. Okay, so this dp के भयो, dp by dt भयो, and this is by c यता गयो हैन, c यता गयो. सो अब यो के गर्छु, dt लाई मैले के लेख्न मिल्छ, I can write it as alpha dr. Okay, I can write it as alpha dr. Okay, so यो नेगेटिभ भ्यालु कहाँबाट आयो फेरि. Okay, so nothing has been changed. यो सबै मैले के गरेँ, 4 पाई r स्क्वायर गरेँ, dpv by d यसको ठाउँमा के हुने भयो, minus alpha dr. Okay, so this is actually minus alpha dr. This is equal to minus 4 pi r square upon alpha dp by dr. Okay, now 4 pi r square चाहिँ म lr को तल लिन्छु. Okay, so lr upon 4 pi r square. अब यता के हुने भयो, यता c अल्फा हुने भयो, then dp by dr. Okay, so since alpha can be written as, alpha को value के हुन्छ, it can be written as mass absorption coefficient and then density. Okay, and dp by dr मैले के भन्थे, p यो जुन 1 by 3 a to the power 4 छ नि, यसलाई चाहिँ if in case मैले यो डिलिट गरेँ. Okay, so if in case मैले यसलाई dp by dr को टर्ममा यदि लग्यो भने यो के हुन्छ, 1 by 3 a 4 आउँछ, t to the power क्युब हुने भयो, then dt by dr. Okay, यो भ्यालु चाहिँ म कहाँ सब्स्टिट्युट गर्छु, मैले dp by dr को ठाउँमा सब्स्टिट्युट गरिसकेपछि then I'll get यहाँ नेगेटिभ छ अगाडि, 3k rho upon 4ac. Okay, no, this is totally wrong. ठ्याक्कै यसको अपोजिट हुन्छ. That will be equivalent to minus c by k rho. Okay, अल्फा को ठाउँमा मैले त्यो सब्स्टिट्युट गरेँ, dp को ठाउँमा 4 by a3 t cube dt by dr. Now dt by dr is equal to minus 3k rho 4ac. This is all r. Okay, अब यो सब भ्यालु मैले यता लगेँ है त. This is 4 pi r square. So this is the radiative temperature gradient. So how do I find the constitutive, that is temperature gradient constitutive. Constitutive को लागि चाहिँ we take the help from the adiabatic constant. So pv is gamma is equal to, we know it is constant. Similarly tv gamma minus 1 is also constant. So from this result I can conclude that t is directly proportional to p and 1 minus 1 by gamma. Okay, now I can write a constant a. Okay, so p 1 minus 1 by gamma. So this is equivalent to a p. Okay, so p 1 minus gamma चाहिँ कता जान्छ, तल जान्छ gamma. यो चाहिँ पछि काम लाग्छ है त. So p 1 by gamma is equal to a p by t. So this is equation 1. I'll use this equation in the later part. Okay, अब यो जुन dt छ, यो पार्ट छ, यसलाई चाहिँ मैले डेरिभेटिभ लगेँ के को टर्ममा, r को टर्ममा, that's it, dr. a 1 minus 1 by gamma p 1 minus 1 by gamma minus 1. यो काट्यो. Okay, so it is a 1 minus 1 by gamma र p 1 by gamma, p 1 by gamma को ठाउँमा के लेख्न मिल्छ, okay, since it is minus 1 by gamma, so 1 by p 1 by gamma. So it is given as 1 minus 1 by gamma. अब p gamma भनेपछि ap by t हो, t माथि जाने भयो, ap हुने भयो, f4. So So यो काट्यो, so it is given as T by P 1 minus 1 by gamma, र गामाको ठाउँमा I can write it is given as Cp by Cv. So our final answer will be dt upon dr T by P 1 minus Cp by Cv, that is Cv by Cp. So this is the constitutive energy transport that we will get. Okay, so this is the case. I hope you guys get this derivation. Try garnus. Okay, you will get the exact same time. So these are the two very important questions that will be asked. So to give you a general idea, so radiation is, it is caused by the, it is carried by the photon. Okay, so photon carry the energy from the radiation. And how convection takes place? It is due to the motion of gas. Okay, that is the bulk motion of gas. So how does conduction then take? It is the due to the actual motion of the particle. Okay, so it is the actual motion by the particle. So when you boil the water, the bubble from the bottom of the container rises above, that is the conduction, and from that it is carried out by the convection. Okay, so radiation also involves, but you can just neglect that in case of the boiling water. But from the sun we get the energy by the process of radiation. So I hope you guys get all this है. अब यो चाहिँ एकदम धेरै थियो. So take a time, यो एकचोटि फेरि पढ्नु. Okay, so in this next video I'll talk about the numerical from this chapter, and then our chapter will be finished. Okay, so thank you guys.